Moving deep beneath the surface reveals the sheer scale of the Earth's geological layers. This massive, unbroken matrix of solid rock appears entirely static until we reach a fracture, a tectonic fault line. This cross-section maps the immense physical forces at play. Vector arrows show tectonic plates pushing against each other with unimaginable pressure. Yet the plates are not moving. A boundary layer of static friction completely locks the fault together. We observe continuous, massive tectonic force being applied, paired with a total lack of plate velocity. Because the locked fault prevents physical movement, the kinetic energy driving the plates cannot dissipate. Instead, it accumulates, trapped entirely beneath the surface. To trace where that trapped energy goes, we look away from the fault line itself and focus on the surrounding rock matrix. The solid rock absorbs this potential energy through a mechanism known as elastic strain. This 3D block model isolates that process. The pulsing red overlay visualizes the increasing concentration of elastic strain energy, showing how the rock layers physically deform and bend without breaking. Under this accumulating strain, the geological layer acts exactly like a highly compressed mechanical spring. But rock has strict physical limits. It can only bend so far before the internal stress finally exceeds the static friction locking the fault. When that structural limit is reached, the rock suddenly snaps back to its unstressed baseline geometry, a process known as elastic rebound. An earthquake, therefore, is the inevitable, violently rapid physical return of deformed rock to its original shape. Returning to our 3D crust model, we can pinpoint the exact subterranean moment static friction fails. This localized 3D coordinate of initial rupture is defined as the focus, or hypocenter, starting our timeline at exactly T0. At this precise second, an instantaneous phase change occurs. Decades of stored potential strain are instantly converted into kinetic energy. That kinetic energy radiates outward from the hypocenter into the surrounding rock as fast-moving, concentric mechanical body waves. As it travels through the deep earth, this radiating energy automatically partitions into distinct wave phases based on the physical density of the subterranean rock. The precise depth and location of this single node dictates the velocity, geometry, and timeline of all the surface destruction that follows. We look first at the leading edge of this expanding energy front. The fastest propagating phase of the seismic release is the primary wave, or P wave. This macro view isolates the specific longitudinal mechanics of the P wave. Notice the fast push-pull compression moving strictly parallel to the direction of wave travel. This accordion-like motion efficiently translates kinetic energy through dense, solid materials with minimal physical resistance. Because compressional energy transfers so rapidly, P waves arrive first, serving as the ultra-fast, albeit less destructive, initial warning of a deep rupture. Immediately trailing the primary wavefront is the second phase of the energy transfer. These are the slower secondary waves, or S waves. Looking again at the rock texture, we see the transverse kinematics of the S wave. Unlike the push-pull of the P wave, S waves travel with a distinct up and down shear motion that runs entirely perpendicular to their path of travel. These shearing mechanics face higher resistance within the rock matrix, causing S waves to inherently lag behind compressional waves. However, this slower transverse motion carries vastly higher amplitudes, generating significantly more destructive potential. The growing chronological gap between the arrival of the P waves and S waves represents the only physical lead time a surface location has before peak subterranean destructive energy hits. The destructive subterranean transit finally concludes when the rapidly expanding body waves violently breach the surface of the Earth. The 2D geographic coordinate located directly above the rupture focus is defined as the epicenter. When these deep body waves strike the Earth's surface boundary, they undergo a physical conversion into highly complex surface waves. Once the energy reaches the surface, the resulting destruction is dictated almost entirely by local geotechnical soil conditions. The epicenter functions as a critical energy conversion zone. Here, fast underground kinematics transform into localized, catastrophic surface hazards. Consider an urban area built on loose, saturated, and unconsolidated soil. When violent S-wave shaking interacts with this waterlogged matrix, the soil mechanics rapidly destabilize. This microscopic cross-section illustrates the process. Continuous, rapid shaking causes the pore water pressure between the individual soil particles to dramatically increase. This forces the particles apart, causing the soil to lose its effective stress in a state known as soil liquefaction. On a macroscopic scale, the solid ground temporarily acts as a thick, viscous liquid, completely losing its shear strength. In liquefaction zones, structural failure is rarely caused by the physical impact of waves shattering concrete. Instead, the ground entirely loses its mechanical capacity to support mass, causing intact buildings to sink directly into the earth. To observe a stark geotechnical contrast, we shift to a coastal city grid built directly on solid, dense bedrock. While bedrock does not undergo liquefaction, it provides an ideal medium for transmitting high-amplitude surface waves. At the surface boundary of solid rock, the energy organizes into specific waveforms known as Love and Rayleigh waves. This split-screen visual compares the simultaneous destruction mechanisms. While the left screen shows intact buildings sinking into liquefied mud, the right screen shows high-amplitude surface waves physically rippling the solid ground like ocean swells. The rolling swells and horizontal shearing motion of these surface waves uniquely exploit the brittle lateral weakness of rigid structural foundations, violently shifting buildings off their bases. Catastrophic earthquake failure varies drastically by location. Specific wave kinematics dynamically exploit the exact mechanical vulnerabilities of the Earth directly beneath our feet.